Okay. Well, thanks everybody. Welcome. Thanks for coming, and thanks in particular to you, Aino Teşekkürler, for inviting me here. And it's my first time actually that I'm giving a talk here. It's nice. Yeah, I'm going to speak about, as you just said, about uniqueness and non-degeneracy results for some nonlinear equations. And the particular feature that these equations have is that they don't involve the Laplacian, as is what's typically the classical case, but a fractional power of the Laplacian. Okay, so therefore we have non-local effects, and I've been working on this project jointly with Enno Lenzmann for at least 4 years. And then you see it already, I mean, from the date. So you see that preprint, that was our old paper that was submitted in fall 2010. And since then, we've been stuck on this problem. And I'm very excited that today I can present some recent progress. Actually, this summer, I think there was some kind of breakthrough that we managed to extend this result to the n-dimensional case, the general case. And even if you're not really interested in these nonlinear questions, there is behind it is a result about a linear Schrödinger equation, or the eigenfunctions of a linear Schrödinger equation, or fractional Schrödinger equation, I should say. And we had to understand that better to make progress in this nonlinear problem. And that's somehow the goal of this talk, to explain these things to you. And let's see. And then I should also mention that while in these 2 years, while we were stuck, we joined forces with Luis Silvestre from Chicago, who had an idea to extend our one-dimensional result to some higher dimensions. And that was, again, about a year and a half ago. And then finally, we could combine this Luis idea together with what Enno and I did. And that's to come later in the talk. But let me start with the beginning, okay? So let me start with some classical results. Yes, the question already?
The beginning is to explain why in the world you want to look at this equation.
Oh, that comes on slide 3, I think.
Oh.
Okay, it will come. And well, I guess it's because you gave it to Enno as a thesis project. Yes, right. But you will see, I mean, even if some people like an S which 1/2, there is no S yet. But even if some people will like the S equal to 1/2 better, then you will see in our argument that we need to do it for any S. It's not just mathematical curiosity, it's really something we need. Anyway, so let me start with the classical case to set the picture. So we have an equation like this. Okay, it's minus Laplacian q. There's minus q to the alpha plus 1 equal to minus q. That's like a nonlinear Schrödinger equation with an eigenvalue equal to minus 1. And the point is that the potential is a power of the ground state itself. Okay, equations like this come up in a lot of physical problems. You might have heard about these Gross-Pitayevsky things. In this case, it would be a negative scattering length. This would be the case of the cubic equation. I think if in more general models, I've heard that a fifth power is included when you have 3 particle effects. And another case where this equation comes up, that's q to the, I think, 3/2. That's in the description of Bose condensates, and a two-component charge Bose gas. But anyway, I think this is just the kind of simplest nonlinear equation you can look at. And so I think it's a natural testing ground for the methods and tools that are available before one looks at more complicated models. So we will always be looking at this equation on all of Rn. And we will be interested in finite energy solutions. So in other words, all our solutions tend to 0 at infinity. Okay? And then the functions are supposed to be positive. That means that they are kind of ground states in a system, and then these functions are automatically positive. Okay? then there's this number alpha appearing in the equation, which is the strength of the nonlinearity, and the only assumption that we will make is that this number is subcritical in the sense of Sobolev embedding theorems. Okay, so this depends now a little bit on the dimension. You see there is no restrictions in dimension 1 and 2. There is a certain restriction in high dimensions, but the point is that the equation just doesn't have any finite energy solutions if this is not fulfilled. Okay, so just that's...
When you say energy, is it anything?
Well, I mean the integral of the gradient of q squared, the Dirichlet integral of the function, and also the L2 norm. Okay. Good. Okay. Now there are, I think, 3 important results on this equation. Now the first question that you ask is there a solution at all, right? Because it's a nonlinear equation, that's not so easy. And, well, how does one produce a solution? Well, you look at something, a quotient that appears in the Sobolev inequality, right? So you have the 2 norm of the gradient, you have the 2 norm of the function, and you take a mean of those. This you raise to the power theta, this to the power 1 minus theta. And then you say, Sobolev tells you that this is bigger than some power bigger than 2, right, alpha plus 2 of the function. So a Sobolev inequality tells you that this thing, the infimum of this over all u, is always strictly positive. So now you can look at a minimizing sequence, and then people in the mid-70s, and I should mention in particular Strauss here in 76, who proved that a minimizing sequence converges for this. Okay, and then if you rescale, then look at the Euler-Lagrange equation for this thing, right? Then, so if you think about minimizing the gradient term, this gives you a minus Laplacian, and these 2 things, they give you Lagrange multiplier. These are these 2 things over there. And then just by a simple rescaling and multiplying by a constant, you get, then you can set both Lagrange multipliers to be equal to 1. Okay? So this settles the issue of having actually a solution. And anyway, one can also prove that any solution you get by minimizing is necessarily a positive solution. Good, so we got a solution. That's fine. So the next thing is, what can we say about these solutions? And what we would like to have, right? So this thing here is a translation invariant problem, right? Because all the norms are over all of Rn, nothing changes if I translate the thing. Now, of course, having existence of a minimizer means that translation invariance has to be broken. Now, the other point is you have also a rotation invariance, right? Nothing changes if you rotate the thing. Now, the difference, of course, between translations and rotations is that translations are non-compact symmetry, rotations are compact. So therefore, you would expect that rotation symmetry is not broken. And that's actually the second kind of result, which goes back in the Russian literature to Alexandrov. And then it was Jim Sarin who made it popular at the end of the 50s in the West. And then again, so the really famous paper about this is Gieders-Nirenberg in 83, where they showed for a much larger class than this equations. But generally, nonlinear translation invariant nonlinear equations, they showed that positivity of the solution alone implies symmetry. Okay? So that's stronger than what you might get from rearrangement inequalities of things, because rearrangement inequality just tell you that there are symmetric solutions, but there could be also other ones, right? So you really need somehow a symmetry result that you have that you see that this symmetry is not broken. All right. Now, at this point, you might say you're essentially done, because now you've reduced everything to an ODE, right? So this Laplacian just becomes twice the second radial derivative plus n minus 1 over r, no, 1 radial derivative. Now that is, however, a non-autonomous equation, and so in general you can't say much about this, and this is actually one of the points where it really becomes hard, the problem. And there are again results by, so this has been studied a long time ago, Kaufman, McLeod, Sarin, and then Kwong. And notice after Kwong I didn't put any points, because Kwong really got the definite result there. All the other results have been refined afterwards and so on. Kwong really showed that the solution to this equation is unique. Once it's radial and positive, it is unique. And that's really, even though it is only ODE, it's really a hard piece, and it's really where the work is. And so these existence, symmetry, and uniqueness, those are the basic results about this equation. And just to give you a small side remark, I said that the equation has to be subcritical in the Sobolev sense, which meant that there is a strict inequality there. You might also ask about the case when you have equality there. But then you see from a simple dilation argument, now the two terms scale the same, that you better don't want to have a right-hand side. Okay, so the equation in the critical case would become that one, and there it turns out that you can classify all the solutions. That's the equation that comes out when you look at the Sobolev constant and the optimizer in the Sobolev constant. But that's a completely different story. Okay, you can just write it down. The point here is you have to work with some unknown function and you have to prove that this is unique. Okay, so that was a bit of a review what is known in the case where we have a Laplacian. Now what we're going to do here on the next slide is essentially the same equation, except that I put a to the power s there. So what does that mean? Let us remind this. You go to Fourier space, and in Fourier space, you multiply now by xi to the 2s. When there was a Laplacian was xi to the 2. Now it's xi to the 2s. Good. Okay? And so that defines an operator. And you see from this expression immediately that it's a non-local operator. What happens over here can affect the solution over there. Okay? And this power s that appears there will always be between 0 and 1, and that's really a crucial thing, and I try to explain you later on why this is, I think, the only case where you can expect something. Okay? Otherwise, the form of the equation does not change. Alpha, as I said before, has to be subcritical in the Sobolev sense. Now the numbers here change a little bit, but not this. I mean, the idea is still the same, and we're still looking at non-negative or positive solutions to that equation. Okay. And again, we're requiring finite energy. And now there were 3 steps on the previous slide: the existence and the symmetry. Those were the first 2, and I'm telling you here that those things work exactly the same way as in the usual case. Okay, so all these compactness arguments that the things are compact up to a translation, they work here for this power, and this method of moving planes, this Gieders-Nienberg method, also can be adapted to this case. And that's already where the assumption s between 0 and 1 comes in. Okay. Now, how about the third step, the uniqueness part? Now you again arrive at a one-dimensional equation, right? It's a radial function, so you can write down this operator on the half-line. But the point is still it's a non-local equation now, so it's not like an ODE that you have a value and a derivative and then you can solve uniquely in the forward direction. It's a non-local equation on the half-line where what's out there can influence what's in here. Okay, and so we have to understand what's happening there. And that's, I think, the point where I want to start in this talk and the question that I want to answer. Now, I should tell you about what has been known before, and actually there is not much. I mean, you see there are 2 parameters, 3, I mean, there's a dimension, there's the power s, and there's the power alpha. And there's exactly 1 value, so dimension 1, s equal to 1/2, alpha equal to 1. Only that case was previously considered, and just it turned out that once again you can write down the solution. And you know, once you have it, then you can, if you know the solution, showing uniqueness of a thing you have is of course a lot simpler than showing uniqueness of something which you only know exists. Okay, so that was a paper by Amick and Toland, where in this case the equation appears in the context of water waves. Exactly. So the fact that I'm always talking about positive solution, that means the ground state.
But do they
Morally.
more than that?
No, they only get the ground state. Right. Right. And once again, if you go to the Sobolev critical case, so you take the alpha to be equal to the one that I just excluded, then once again you can write down the solutions, and then the thing you can solve it by hand. And so that was done in the energy sense by Lieb, and then by Yan Li and by Chen Liu in the really for classification of all the solutions. But that's a different story. Okay. So now the question, what is this good for? Why do I care about this? Okay, that's the third slide. So really, I know that this is a stationary equation. There was only an x dependence there. But this is really important, or comes up when you look at time-dependent equations as well. So I've written down here 3 different time-dependent equations. The first ones are in 1 + 1 dimension. The second one is in 1 + general n dimensions. Okay? And so one is the Benjamin-Ono equation, which appears in these water wave models. And then Benjamin-Bohner-Mahoney equation, it's perhaps not so well known. And then there is a fractional nonlinear Schrödinger equation, which again is perhaps again more familiar. Now, the point is that these dispersive equations have a special class of solutions, which I can get from my stationary solutions. And that's what I've written down here. So here are 3 solutions. Right? So here in the first case, for the generalized Benjamin-Ono, what you do is you look at the traveling wave. That's x plus a multiple of t. So this thing just moves as time goes on. And the function q here, so such that this guy solves the equation from before, has to be a solution of the stationary equation. Okay? So just for any c you pick, you get a traveling wave solution of that. Similarly here, for example, in NLS, there you do a rescaling, and the time dependence is just on a phase out there. Okay, so these solutions are, of course, special solutions for these equations. And now when you study these equations, it depends a little bit on how smooth they are. So in the more regular case, you ask questions whether these solutions are stable. If you start close to such a solitary wave, do you always stay close to such a solitary wave? This is closely related to the question of non-degeneracy, which I haven't mentioned, but which is essentially the same as uniqueness. Okay? Now, the other thing is when the equations are rougher. For example, here in the NLS equation, if this power alpha is large enough, then the solutions do not exist for all times. But there's a phenomenon called finite time blow-up. And now you might ask yourself, how does this blow-up occur? And the fact is that at least if the mass is not too big, all the mass will concentrate at one single point. And now you zoom into that point, and you look how the thing looks close to the blow-up point. And then it turns out once again that this uniqueness and the non-degeneracy is crucial to really understand how this mass concentrates and what the profile is. So that's actually a topic which is, I think, rather hot today, and there are many unsolved conjectures about this, in particular concerning, for example, if you have blow-up at several points, and what goes under the name of soliton resolution conjecture. Anyway, so this uniqueness is certainly a non-degeneracy, is a first step to doing things like that. Yes?
Are there any results known for the Hartley case?
That's, of course, something that, right. So, so the question is, what we're making here a simplification. We're looking here at a local nonlinearity. So even though the kinetic energy is non-local, here we say somehow that the u only sees a potential which depends on the u at a point. You can write down another equation, which is also translation variant, where instead of taking here, say, u squared, you write u squared convolved with some symmetric decreasing kernel. And you wonder what happens there. And so that is actually, that appears, for example, in the description of boson stars. And that's actually one of these cases that we would like to study, and where we believe actually that our techniques are helpful, are useful, because the signs go the right way. And well, since I told you that what I'm telling you here is about 6 weeks old, or perhaps 4 weeks old, we are at the moment very busy writing this up, but we certainly have always the boson star in mind. And No, absolutely. Right, so those are the same questions. Actually, here is the boson star, so that's okay. So looking apart from these time-dependent motivations, I guess the uniqueness questions have been asked by several authors in the literature, mostly concerned with these water wave phenomena, for example, Weinstein in 1987, and also quite recently Koenig, Martello, and Robbiano in 2010. And they, I mean, just everybody believes that the ground state should be unique, and they always conjectured this, but there haven't been any results. And Lieb and Yao also in 1987 asked the questions in this case with a non-local nonlinearity, but both terms are non-local. Okay, but I think, I mean, apart from all these applications, I think there's also something to be understood on a fundamental mathematical level. I mean, just the question, where does this uniqueness come from? And just to start this whole thing, it's perhaps good to look at a linear Schrödinger equation, okay? So where this term here is just a potential V, and then you ask yourselves, under which conditions is the ground state unique? And I'm looking at, I don't have any symmetry restrictions. And then it turns out that the uniqueness for this ground state is closely related, essentially equivalent to the positivity of the heat kernel. Okay? And the positivity of the heat kernel, you have that only between 0 and 1. So that's really a fact. And again, the positivity of the heat kernel, that's always related to a maximum principle for the equation. So these things somehow go hand in hand, and that's kind of what we want to uncover here. And because, you know, uniqueness should not be a result which comes from some ODE techniques, right? Uniqueness does not really have anything to do with locality somehow, but should be rather more general phenomenon coming from maximum type principles. Okay.
Linear Schrödinger.
Exactly. Exactly. But for Perron-Frobenius, you need the positivity of the heat kernel, and therefore you need this assumption. And that's also the point, I mean, why all these results, why we only look at this case. Otherwise, the solutions can have arbitrary sign. Okay? So that's this. Well, perhaps I should say a few words, I mean, about general motivations where these non-local equations come up. So I guess in mathematical physics, the typical thing is when you want to include relativistic effects, where the energy grows only linearly with the momentum for large momenta. That's also, again, that's another simplification of what we're doing here. We're setting the mass equal to 0 in that model. But as I said, we're going step by step towards the full problem. You also find it, I understand, in mathematical finance, where you know you want to look at extreme or rare events. Now, the heat kernel for the Laplacian, this you remember, that's a Gaussian. So that's really very, very small. So the probability that something unlikely happens is suppressed super exponentially fast. Now, on the other hand, when you look at the heat kernel for any S strictly between 0 and 1, then that decays only polynomially. So this gives a lot more weight to what's out there, and therefore kind of is used, as I understand, to model some unlikely events. And also in mathematical biology, I hear that you use this from time to time to model some non-local phenomena. Anyway, that's what we're looking at. Here I told you that we have kind of a goal. We want to understand something. Unfortunately, we cannot really follow this scheme. So that's kind of, as I tried to explain, we've been working on this for 4 years. We have by now somehow tried everything we could, and eventually we came up with this theorem, which luckily gives an answer to the question, unfortunately does not somehow answer the question I posed at the end, and which somehow I leave you really to think about. But let's look at this main theorem, which, as I said, proves uniqueness and non-degeneracy. Now, the first thing that we have to do is we have to somehow quantify this fact that we are talking about a ground state to the equation. Okay? In the local case that we discussed before, positivity of the function was enough. Now that's, at least in our proof, no longer so nowadays. So what we have to do for our result is we look at, where's that? No. We look at the equation, up there it is. Okay, that's the equation for a non-negative function q. Now we differentiate the equation with respect to q. That gives us a linear operator, right? When you differentiate the nonlinearity, alpha plus 1 drops down. So that's now Schrödinger operator on Rn. Its essential spectrum starts at +1. Okay, so that's somehow up there. And now you define the Morse index of the solution to be the number of strictly negative eigenvalues of this operator. Okay, that's a number of unstable directions. And essentially our notion of ground state is a solution to the equation which has Morse index 1. And I'll explain you later why we believe that this is the correct definition of being a ground state. Okay, and now our theorem says the following. So take any dimension, take any s between 0 and 1, take any alpha for which there is a finite energy solution, right? Then there's a unique up to translations solution of the equation with Morse index 1. Okay, so within all non-negative solutions of Morse index 1, that's the assumption, there is only one and it translates. That's what we're proving. And the second piece, so that's the uniqueness piece, and the second piece, that's the non-degeneracy result, that talks about, well, this guy, so it has one strictly negative eigenvalues. Now, what happens about 0 eigenvalues? And we say there are exactly n of those, and those are only the trivial ones. Right? Where do they come from? Just differentiate the equation up here with respect to one coordinate xj. So you see then you get exactly this thing down, and you see that this derivative lies in the kernel of the linearization. So here they are. The theorem is there is nothing else. Okay, so just the translation invariance of the equation says that there are 0 modes. They don't change the energy. But you can't lower the energy otherwise. I mean, in all other directions, it goes strictly up. That's this theorem that is crucial somehow in when you make this blow-up analysis. Okay, that you have somehow a strict coercivity except from the trivial directions. All right, so as I said, the restrictions on alpha are optimal, on S also, and now we have general dimensions. The result for n equal to 1 was the previous result with Enno Lenzmann, and now the second one is joined both with Enno Lenzmann and Luis Silvestre. And then the question that you might ask, of course, is whether really every positive solution to the equation has Morse index 1. So that is true in the local case. Okay, but the argument is indirect. So you first somehow look at the equation, you first classify them, and afterwards, once you have them, you can check they really all have Morse index 1. But there is no direct proof of this direction. Nevertheless, I think that's an interesting question.
How about the closed form expressions for ground states?
They don't exist. They don't exist. They don't even exist in the local case. So for example, I know Beckner, for example, worked a lot on this ratio, right, where he just had, I think, power 4, 2, 2, and 4 in 2 dimensions. And they tried to get, I mean, they were not looking at the closed form expression for the function, but they were looking at the closed form expression for the energy and getting good upper and lower bounds. So there, I think people have studied this a lot, but they don't know much more than what you can get numerically. Mm-hmm.
I didn't understand what the question was.
No, the question is whether you can write down the functions explicitly. Okay. And so I'm saying you cannot even write down the energy explicitly. You're far away from writing down the function explicitly. Right? But you do know, well, I didn't write it down, but you do know that this function is, well, it's a, I mean, of course, if it's unique, right, it has to be radial, right? Otherwise, you would have a different one by rotation. So it's radial. Also, the proof will show that it's a symmetric decreasing function, okay? Then you know that it's decaying polynomially at a certain rate. So you have kind of information on this. I think for practice, you know quite a lot about it.
Is there any expectation for the every positive solution has Morse index 1? Do you expect?
I guess I would expect, of course, I'm raising the question because I think it is true. Because it's true in the local case, and I think we would also understand better the local proof. I mean, these 40 pages of Quorum's uniqueness proof, we would understand them better if we would know this a priori. But you know, and so that's what I'm going to say now, when you're looking at this from a physical point of view, then your solutions are not any old solutions, but they're energy minimizing solutions. What I'm going to tell you on the next slide is for those we know that they have Morse index 1. Okay, so typically in practice the things that come up satisfy this equation. Okay, so that's what I wrote down here. Remember, in the first slide, I told you how you produce solutions. You look at a quotient like this, you minimize it, and then you rescale and do stuff, and then you get a solution. And I'm saying that the minimize of such a quotient is unique, modulo the symmetries. I'm saying that this is a corollary of that, and of course, to verify this, I have to check the Morse index 1 condition. So let me do that on the next slide. I've written this out in a little bit more detail. Okay, that's the same result as before, except that I spelled out what I meant by modular symmetries. Because see, if I look at an energy quotient, then I have both translation variance and dilation invariance or covariance. Okay, so that's the uniqueness. Anyway, you do the rescaling, the multiplication, you get to this equation. Now, why is the Morse index 1? Well, first thing is you take the expectation, or you just multiply this equation by q and integrate. So that gives you q, the operator LQ, except remember this operator q from differentiating had an alpha plus 1 coming down. So whereas the equation has just a 1, so there's a leftover alpha, so this guy is negative, so the variational principle tells you immediately that this operator has at least one negative eigenvalue. Good. So how do we get the other direction? Well, so by J I denote this quotient. You take Q, you take an infinitesimally small perturbation, and you make a second derivative. And now I know you have all done this before. You write this out, and you'll find that the operator is exactly this L operator plus 3 rank 1 terms, where just the function phi comes together with a different function. Now, when you look at this, you can simplify this using the equation. You can play a little bit around, and then you see in a straightforward way, so there's nothing hidden, that on a subspace of codimension 1, the positivity of the Hessian implies that this L operator is non-negative. Okay? So therefore, this means that you have at most one negative eigenvalue. Okay? So this also means that even a local minimum for this thing, it doesn't have to be the global minimizer, already has Morse index 1. Okay, so therefore I think that this is the natural assumption. Good. So now, right when I started this talk, I mostly spoke about the uniqueness question because that's somehow easiest to explain. Where this non-degeneracy, we had to look at the linearization, talk about this. Now our proof is rather the other way around. For us, the non-degeneracy will be the crucial statement. We will prove that first, and essentially we will deduce uniqueness from the non-degeneracy afterwards. And so the point here of this slide is somehow to use the fact that this solution, right? I said this at the beginning, positive solution is automatically radial. So this is a Schrödinger operator with radial potential. So this commutes with rotations. So you can look at fixed angular momentum. In mathematical language, you look at spherical harmonics of a given degree. And what I want to tell you, the upshot of this slide is that you only want to look at angular momentum 0, only at radial functions. Okay? So why is that? So the first thing, that's what we discussed before. If we differentiate the equation with respect to a variable, then we find that the derivatives are in L+, as in the kernel of L+. Now, since this is the Q is a radial function, how do the derivatives look like? Well, they're just the radial derivative times a spherical harmonic of degree 1. Good. Now, since the function, the solution, is decreasing, the radial derivative here is negative. So we have, on that subspace of angular momentum 1, we have a solution to the equation which has a sign. And then Perron-Frobenius again tells us this has to be the ground state. Okay? So therefore, we know that these guys that we found here on the sector of angular momentum 1 are the ground states. And they are unique. Okay, so we dealt with angular momentum 1. Now how about angular momenta bigger or equal than 2? Well, there you just use that there's a centrifugal term in the equation which somehow drives the energy strictly up. So if 0 is an eigenvalue for L equal to 1, then for the lowest eigenvalue for L equal to 1, the lowest eigenvalues for all higher L are strictly above. So we have certainly no body lying in the kernel which has L bigger or equal than 2. Good. So we're left with L equal to 1, or in other words, just look at this operator on acting on radial functions. The argument I told you before is on that space, we certainly have one negative eigenvalue. And now here comes the non-degeneracy statement as we will use it. Okay? We say that if we know that this radial operator has exactly one strictly negative eigenvalue, then 0 is not an eigenvalue. Okay? So that's kind of magic, right? You know something about negative eigenvalues, and then 0 has to cannot be an eigenvalue either. So you can think of it, if you want, in terms of ordering of levels, right? So you have the S waves are eigenvalues 0. Sorry, the P waves are eigenvalues 0. So you want to have the second S wave above the first, second S wave above the first P wave, right? But I don't know. We never got anywhere with this in this ordering of levels. Well, idea. Anyway, so you agree, I think, that once I've proven this, I've proven the non-degeneracy part of the theorem. And what I'm going to explain you next is, if you have this non-degeneracy theorem, then you actually get also the uniqueness part. Okay? So I'm saying, if I can control the infinitesimal change, the linearization of the equation and its 0 eigenvalues, then I can really control the global uniqueness of the problem. Okay? And that's done by an implicit function theorem. And that's the point where even if we are mostly interested in s equal to 1/2, we have to go to every other value of s. Okay? So what we're going to do is we fix our s0 value. That's the value we're really interested in. Okay? And we start with the solution Q of this equation. And we're assuming that this has Morse index 1. Okay? And then by first time we apply non-degeneracy, we learn that nobody's in the kernel. So this means now we can apply the implicit function theorem with respect to s. S is our parameter. And we construct a solution to this equation for s close by the s0 we had. The alpha we keep fixed. Okay? And these functions depend continuously in this norm of L2 intersected with L alpha plus 2. Well, in some sense, it's a nice curve, okay? And it exists at least locally because we have this no 0 eigenvalue. This means that we can invert the operator, okay? Good. Now, this branch has a few nice properties. If we started out with a positive function and it was also decreasing, then this is preserved along the flow. That's good. Now, see, the main point is because of this non-degeneracy result, this says, look at it, we always have a negative eigenvalue. Now let's look at the second eigenvalue. The point is somehow the negative eigenvalue never goes up because there always has to be a negative one. Now the second one up here can never go down, right? Because the non-degeneracy says if we only have one down, then 0 is not an eigenvalue. So somehow they can't cross, the second one can't cross. So 0 is never in the spectrum, so we can continue this branch and continue. It never stops because of that. Okay? And so I'm claiming here, and I'll talk a little bit about this more, that we can really continue this branch all the way up to s equal to 1. And that's good because, as I told you on my very first slide, for s equal to 1, we know it. So it's kind of unfortunate that here I'm using this ODE result, which I did not want to use. But anyway, what do you do? So you go to S equal to 1, you have there the unique solution. So no matter where you started at your S naught, you're connecting to one fixed guy. And at S equal to 1, well, the guy is not only unique, but it's also non-degenerate. So you can also go backwards. And so if you had two different branches connecting to the same thing, then you would get a contradiction there, right? Because there is only a unique path. That's the argument. Okay? So now, of course, there was one point I was being a little bit fast here, and that was the one, well, these functions can do some funny things when you make the go along the branch. It could just be that, say, the thing just converges to 0, just disappears, right? 0 is also a solution to the equation. So you kind of, when you approach, the argument is like you define the S star, that's the largest S up to which you can continue. And then you have to use some compactness arguments to say that at this S star, nothing bad happens. Okay, now that's an exercise in calculus of variations. So first of all, what you have is you have, of course, an energy identity, right? By just integrating the equation against Q. We did that before. Then you get a relation between the three quantities, the kinetic energy, the nonlinear term, and the L2 norm. Now there's another thing, an identity, which is called the Poroshaev identity, which gives you yet another relation between the three things. Okay, and then you play with the identities and Sobolev inequalities, and then you get a lot of good bounds, and the only thing that's left to say is an upper bound on QS, on the 2 norm. Okay, so that's, in other words, you want to avoid that this function goes down to 0, vanishes as you approach this critical value. And, well, at this point you have to work a bit. You have to use a Gronwald type identity, so you differentiate along this curve, and you, what do you want to say? You really have to use a little bit of elliptic regularity. So there you leave the energy world, but you really work with the equation, and you bootstrap a little bit out of regularity, and that's the ingredient. Anyway, so once you've done this, you have by a compactness constructed a solution at S star. Now you do the same argument. At S star, you cannot have a 0 eigenvalue because you have a negative eigenvalue. You always know that. And therefore, you have to be able to continue. So that's the argument what's in there. Okay? So now, at this point, I've reduced everything to the proof of this non-degeneracy statement. And at the beginning, I've promised you that we need to understand the linear Schrödinger equation better to answer that. And that's exactly where we are now. Okay? So now let's forget all this nonlinear stuff. Look at the linear Schrödinger equation. I guess I didn't even write it down. So this linear Schrödinger operator is minus Laplacian to the S plus V. Okay? This operator has a lot of the properties as the usual Schrödinger operator has. It has a couple of discrete eigenvalues and perhaps some essential spectrum afterwards. We said already at the beginning that we know that the ground state of this operator is a strictly positive function, and it's unique. Good, this we know. Now the question that comes in here is, what does the second eigenfunction do? It's kind of a bit surprising, right? I'm asking about uniqueness somehow, which is always, it's of a ground state, which is the lowest one. But in this non-degeneracy proof, we really have to understand the second eigenvalue. Okay? And now there's an old theorem which goes back to, I think, Courant, or perhaps it's even older, from the first half of the last century, which tells you that for an ordinary Schrödinger operator, you only have, well, you have two nodal domains, meaning the function is a continuous function, and it's, if you look at the 0 set, then it divides space into two connected pieces. One where it's positive, one where it's negative. Okay? So the point is somehow, because it has to be orthogonal to the ground state, which is a strictly positive function, it has to change sign. But it does not change sign more often than it has to. And you prove this, for example, by unique continuation. Somehow imagine it would have three connected nodal domains, and then you just make it equal to 0 and you multiply it by different constants in the other sets. Okay? And then you could get the same energy, but you have now found a function which is identically 0 in some set, which is impossible, contradicts unique continuation. Anyway, the point is we would like to have something like this for the fractional Schrödinger operator. Courant even tells you that the eigenfunction corresponding to the kth eigenvalue has at most k nodal domains. Right? So even this should be true. But we are, I mean, at this moment, just modest, and we want to talk about the second eigenfunction. And that's what this theorem tells us. And by the way, I formulated things now on the whole space. Really, I'm interested in the operator on the radial sector, just acting on radial functions. They kind of go hand in hand. Okay, so let's look. And here's our assumption. Courant doesn't have any assumption. We unfortunately do have it. So we want to have the potential to be a radial function, first of all. But even worse than that, we want to have the potential an increasing function. Well, you might think the Coulomb potential is increasing, the harmonic oscillator is increasing, so everybody's increasing. Not quite so, but it's enough for this purpose. Okay, so for the application, I think it's okay. But anyway, that's where we are. Now, let's look at this operator, again, on the subspace of radial functions. Look at its second eigenvalue on the sector of radial functions. Take a corresponding eigenfunction. And then the theorem is that this eigenfunction has a single node on the half line, and the eigenvalue is simple. Okay? And, well, as I just said, I mean, we would like to have something like this also for higher eigenvalues. We have some results if we look at our proof. In particular, simplicity is true for all the eigenvalues. And it's kind of amazing that this question has not been asked before, except in one special case, namely in one dimension, where you look at the problem on an interval, right, where the potential is infinitely high outside. And there, I think people know by now that the third eigenvalue is simple. But that's really the state of knowledge that there is, or that you have the eigenfunctions are alternatingly even odd. But I think there's nothing known in there. So this is work by Rodrigo Bañuelos and co-authors, and by Kwasniewski. And so even for the higher dimensional case just of a ball, right, the fractional Dirichlet Laplacian on a ball, this is a new result. Okay, so how do we get this? There is an argument in the game which means that you can make this operator local in a certain sense by adding an additional dimension. So x is the dimension we had. So sorry, there's a typo. X runs through Rn. And then we add a half line, which I called y here. Okay? And then what you do is you have a local energy. That's a gradient with both respect to x and y. You put some weight in, which for s equal to 1/2, which we like, you don't have to care about. Okay? It's an operator on the upper half space, which has a potential living just on the boundary of it. Okay? And now you do the ordinary thing. You normalize your function, well, on the boundary, and you minimize under an orthogonality constraint on the boundary. And the point is that this gives you the kth eigenvalue of your Schrödinger operator. When you think about that, it's actually not so complicated, because what you can do is you first write everything else, this term, and that term. This only depends on the trace. So first of all, you can minimize the first term given the value on the boundary. And this you can carry out explicitly, and you do the computation, right? And then you find that you get exactly this fractional kinetic energy on the boundary. Okay? So there's really not much in there, even though we haven't found that in the literature before. Okay, so what good is that? Now you have a local kinetic energy. That's good, because now you can play the Courant game, right? I just told you, you take the function, you somehow, if it had too many nodal domains, say the third eigenfunction, if it had three nodal domains, you would just make it equal to 0 on one nodal domain, play with the constant in the other two, and you get a contradiction to unique continuation. Because then you get a solution of an equation which is identically 0 on an open set. Good. Now this sounds simple, but it's not simple. Because now you know that this extension the u, the function of x and y, has only two nodal domains. But what does this mean for the function you're really interested in, the function down there? And that's a topological thing now. See, when you're in one dimension, that was the point where we were stuck for all these years. In two dimensions, when you have, so that's the upper half space, that's the x variable, that's the y variable. Now in the upper half space we have two nodal domains, plus here, minus there. And that's good because on the line you only have one node. Now let's look at the same picture in 2 dimensions down there, right? So there. Now you could have this one, you see, and you can rotate this around. You see the picture? It's when you look at the upper half space, it's still only 2 domains. It's this donut that goes around. Inside the donut, it's, I don't know, minus, outside it's plus. But when you look at the line, then you have 2 nodes. And we want to prove that the second eigenfunction only has 1 node on the line. Okay? So what I'm saying here, this formula, that's enough for 1 dimension. But for 2 dimensions and higher, you have to work harder. And that's now here, this lemma, this new thing that we could prove, which really solves that case. Okay? So let's look at that. So again, we are in this situation where we are radial increasing potential V. And we look at the kth eigenfunction, or the eigenfunction to the kth eigenvalue in the radial sector. And I'm telling you that the function does not vanish at the origin. See, in the ordinary world, in the local world, that's clear because it's a radial function, so you have a Neumann condition. And so if it would vanish, then both the function and the derivative would be 0, so would be identically 0. Now this thing tells you that the same thing holds also in the general case. And, well, so of course this immediately gives you simplicity of all the eigenvalues. Right? Just take 2 eigenfunctions, assume it's degenerate, take a linear combination, then you can make them vanish, and so therefore the function has to be identically 0. Okay? So that gives you simplicity. Now, I'm telling you it also gives you this thing about sign change. Now, they have to think a little bit more. So imagine you are in this picture. And now what we do is we deform the potential. Okay, so again, we look at a curve of, I don't know, either the power s changes or the potential changes. And then these 2 points will change. And now what we can do is we can rule out that the 2 nodes come together, at least when they come together on the line. So we can exclude a double 0 on the positive half line. But what this thing tells us, it excludes that this 0 goes over there. That's kind of what you write, so you deform. Actually, we can also exclude that it goes out to infinity, so the only case you have to consider is that this node goes into 0, and that's excluded by that theorem, or by that lemma. Okay, and now this proof here is, I think, well, quite surprising, and so let's go through that again. And just to simplify things, I've written it down only for s equal to 1/2, because that makes it a little bit simpler. Okay? So that's the thing we're looking at. That's similar to the last slide, except I changed the t to the y to t. Okay? So x is your n-dimensional variable, and t is your additional 1-dimensional variable. Now you run the heat semigroup for minus Laplacian up to time t. Okay? So this defines your function of 2 variables. Now I'm claiming that this is a harmonic function on the upper half space. It's not hard to do, right? You differentiate twice with x, so that commutes through. And when you differentiate twice with respect to t, you bring down a square root, you bring it down once again, and the 2 terms cancel each other, so it's harmonic. Good. Now let's look at what happens if I look at the boundary derivative at t equal to 0, right? So I differentiate. This brings down a square root. And then I take t equal to 0 at the boundary, so I have exactly the square root of the Laplacian on the boundary, and then I use the equation, and that's what I have. Okay, so that was the sense in which I made the equation local. Good. So I have this equation in the upper half space, that on the boundary of it. And now we look at a certain quantity, and that's, well, somehow there is a paper of Cabré-Cyr where they look, it's a they have a nonlinear paper, and they look at this de Giorgi problem, I mean, of layer solutions which are monotone with respect to one dimension. Anyway, so somehow there is a quantity like that, which looks a little bit like a Hamiltonian, right? It's a dtu squared Vr, sorry. Well, no, I guess I should say it the other way around. It looks a little bit like a Lagrangian, right? So there's the kinetic energy with respect to the r variable, and now the potential comes in with the wrong sign, the minus sign. Okay. Now, on the other hand, you turn that sign of the derivative in the t direction to a minus. So don't ask me where this comes from. But what you can do with it, you can differentiate it. Okay? And that's actually not difficult. So it's a local quantity with respect to r. And you differentiate it, and then, so when you hit this, there's a dr term and a dr squared term. Okay, that's good. Now, over here, when you differentiate it, you get a dt term and a dt dr term. What you want to do is you want to integrate it over. So that gives you a boundary term in t. Okay, and now there's the dr term with a dt squared. And the sign has changed, remember that? So you get a dr squared term plus a dt squared term. Well, that's good because that's our equation. Except that there is this radial term, so that's what I've written down here. Okay, so that's the n minus 1 over r, which you know comes from the radial derivative. Good. And then there was this term which comes from the boundary. Okay, that cancels exactly the Vr term times the u times ur. Okay, that's by using this equation. So the only thing that's left is the radial derivative of the potential alone. But now look at this. The first quantity obviously is negative. And now if v is an increasing function, then the second thing with the minus sign is also negative. So the whole thing here is negative, and therefore it's an increasing function. And now you simply write down what it means that the value of 0 is bigger than the value at infinity. Right, at infinity, all these functions vanish at infinity. They're finite energy solutions. So there's nothing at infinity. At 0, well, the radial derivative at 0 is equal to 0, right? Because we're talking about radial functions. Now that thing has a sign. It's minus a square. So we throw it out. And what we have here is something times u at 0. And that thing is strictly bigger than 0. So that square cannot be equal to 0. And that's what I was claiming. As I said, this is a new theorem. I would like to understand this better. I would like to understand somehow how this can be used in other contexts. But for now, it works fabulously. And let me just conclude this talk by tying the things together, how this one node that we have established now really implies the non-degeneracy. Okay? Good. So here we are. I just remind you what it is we want to prove. If we have one strictly negative eigenvalue, then 0 cannot be an eigenvalue either. So, well, assume 0 was an eigenvalue. Call the function psi, and observe that this function satisfies two orthogonality conditions. Now, where does that come from? Right? The operator, just look at, so where are we? So L of psi is equal to 0. Right? That's because psi is an eigenfunction with 0 eigenvalue. Now, by self-adjointness, I can move the L to the other side. I get L plus Q, comma psi. Now do once again this thing. The L plus has this alpha plus 1 in there, whereas the equation for the Q had only a 1 in there, so there's a leftover minus alpha times q to the alpha psi. And so plus 1, sorry. Plus 1. Right? Because there's an alpha from here and another alpha from 1 from there. So that shows you the second orthogonality condition. For the first one, you have to work a little bit more, but essentially it's a similar thing. You can even, there's also a more abstract argument why it holds. Anyway, once you have it, it's true that if you integrate psi q, well, against q to the alpha minus any constant is equal to 0. Now I'm going to choose the constant as the value of q alpha at some r. Okay? But so that's just plain 0. Good. Now, as I said, I want to choose this r in a good way. How do you do this? Well, I know from what I had before that I have a single 0, a single node of my eigenfunction. So I'm choosing this r exactly at the point where psi changes sign. Well, that's good, because q is a decreasing function. So if I make this value equal, I mean, this quantity changes sign only once. And if it changes sign exactly at the same place where psi changes sign, then the integral has a fixed sign. Okay? It's positive all the time, and this contradicts my orthogonality condition. And that's a contradiction, and proves the non-degeneracy, and finishes this talk. Thank you very much.